This video is on weak bases, KB, how we calculate quantities dealing with weak bases, and then how we recognize what a weak base is. Okay, so kind of a bold bullet point here. Many substances behave as, I guess, weak bases in water. Most common is ammonia, NH3. And looking at NH3, you might say, that's not a base, because, of course, one thing we recognize as bases are things that contain hydroxide. However, ammonia is a base because when it comes in contact with water, it accepts a H plus from water. So the water gives the H plus, leaving behind OH minus, and perhaps that convinces you that this is definitely a basic situation because of the hydroxide ion. So just like acids had their acid dissociation constant Ka, bases have a base dissociation constant called Kb. And it's written the same way. The concentration of the products over the concentration of the reactants raised to their stoichiometric coefficients. Notice I left out H2O, and that's because it's a liquid. Okay, so don't forget that liquids are left out of Kb, Ka, Kc, Kp, any equilibrium expression. Okay, so that's how you would write a Kb expression, and we can look them up. They are on the back of your acid dissociation constant, your Ka sheet. If you flip over, there's a much smaller chart, but there are Kb values there. One thing that we're going to say about weak bases, and this is going to come back up later, is that weak bases must contain at least one lone pair to form that bond with the H plus. So that is one common characteristic of weak bases, is that they have a lone pair. So if you were to quickly draw a Lewis structure for NH3, all of a sudden you should go, makes sense why NH3 is a weak base. It's got a lone pair that would reach out and then accept that hydrogen ion, resulting in the ammonium ion, right? Ammonia, ammonium. Two very different things. Base, conjugate acid, right? Okay. So that's your super quick intro to weak bases with Kb. Now let's look at a practice problem. So this says calculate the concentration of OH minus in a 0.15 molar solution of NH3. Okay, so we recognize that NH3 is a weak base. We're going to write our reaction, which is the same one we just had. It's an equilibrium situation. Okay, and I would need to provide you with Kb for this, or we could go to our chart real fast and look it up. But Kb for ammonia is 1.8 times 10 to the negative fifth. So that would need to be provided to you, or you have the ability to look it up. Okay, so anytime we're thinking weak, we know this is going to be an ice chart. And there's one difference here that we have not seen before, which is that we've never been working with liquid water in one of the equations. And so what's going to happen is, remember, H2O as a liquid is not involved in the Kb expression. And so I'm not going to put any information in water into the ice chart, because I don't need any information on water to write the Kb expression. So I'm just going to put a line through water's initial change in equilibrium concentrations, because it's not necessary. So I proceed like normal, right? My initial concentration of the ammonia is 0.15. My initial concentration at time 0 of the products is 0, just like normal. I build my ice chart. We know that the ammonia is going to decrease. The products are going to increase. It's 1 to 1 to 1 by the same amount. Call it X. And this is exactly like an acid ice chart. We're going to make that assumption that X is small. So we're going to call this 0.15, and we're going to substitute these values in for KB. So I'll come over here, I'll write my KB expression. Right, remember, water is excluded, so I set everything into the expression. NH4 plus and OH minus are both represented by X. X times X is X squared. And NH3, we've approximated to be 0.15. So I solve for X. I did this all in one step, so I don't know what the X squared is equal to. I just know it's equal, that X eventually is equal to 1.6 times 10 to the negative third. Whoops. And that'd be a concentration, so molarity. Just like normal, I would want to check this approximation. And remember how you check it, the value of X over the starting. And we're looking for what percentage that is. If it's less than 5, this approximation is fine. It comes out to be like 1.1. So this approximation is good. And let's answer the question. Calculate the concentration of OH minus. Well, OH minus is being represented by X. So the concentration of the hydroxide ion in this case is 1.6 times 10 to the negative third molar. And I have answered the question. They did not ask me to calculate a pH or a POH. I could, but that was not what this question was asking. So I'm done. So this is the same idea as using an ice chart with a weak acid. It's just that this value is different. It's called KB. And then the only other situation is that the water is not part of the KB expression. And so, so I just kind of omit it from the ice chart. Okay. I have no data on it, and it doesn't matter anyway because it's not part of KB. Okay. So second kind of discussion in this video is, well, how do we recognize a weak base? We've already said that a weak base must have a lone pair, but more so than that, what else is there? So that's kind of the first broad category, is that weak bases can be neutral substances with an atom with a lone pair to accept the H plus. And a great example of that is NH3. And again, we showed why. Okay. So that's our first category of a weak base. And then the second category is the anion of weak acids. Okay, so remember, keep in mind that the conjugate base of a weak acid is a weak base. We learned that in a prior lesson. So the conjugate base of any weak acid will behave like a weak base. So let's see, for example, if we just look at any acid, weak acid on my list, like this, HClO. Oh, sorry, that shouldn't have a charge there. Okay, HClO is a weak acid. So if you think about when it ionizes, right, into H plus and ClO minus, this is its conjugate base. And since it's the conjugate base of a weak acid, it's also, we're going to also say it behaves like a weak base. And if that's in our chart, we can look up the value of Kb for that, for this species. Okay, so who's a weak base? Some, not all, some substances who have a lone pair on an atom that can reach out to then accept that H plus. Or the second example would be your conjugate bases of your weak acids, okay? Or even just the ion, right? I should probably stop saying conjugate base because, for example, if we didn't just have this acid, but let's say we had this, which I think comes up in a minute. Yeah. Well, that's an ionic substance, but if it were to ionize, you would get Na plus and ClO minus. Well, ClO minus is the anion of a weak acid. And so that ion would be behaving as a weak base, okay? So those are your two categories. There's one more problem for us to solve, and it kind of deals with that idea. So it says using pH to determine the concentration of a salt, and we're calling it a salt here because notice this is not an acid or a base, this is an ionic substance. All right, a solution made by adding solid sodium hypochlorite, NaClO, to enough water to make 2 liters of a solution has a pH of 10.5. Okay, so it's basic. Calculate the moles of NaClO that were added to the water to begin this whole process. So this is a different kind of question. And we have to kind of think about how we're going to solve this. So I have this equation. They gave me the equation. They gave me Kb. I know that this is going to be my base. It's the ion of a weak acid. And of course, we're producing hydroxide. So, okay, I know this is going to be an ice chart. But right away, you might say, goodness, I have no idea what to put into this ice chart. So there's got to be a number somewhere, and I think we have to think about the number coming from our pH. So think about what we can calculate here. I have a pH of 10.5. I have a pOH of 3.5. And I'm looking for something that I can get out of those numbers to fill into this ice chart, right? Well, hopefully you've already done this and eliminated that it's not going to be anything for the water. And it's going to be the hydroxide, right? The hydroxide is going to come from the pOH. And if I can find that number, then I know the hydroxide concentration and we can kind of work our way backwards. So I can find that by taking 10 to the negative pOH, so 10 to the negative 3.5. And that's going to give me 3.16 times 10 to the negative 4 molar. Well, that's my concentration of the hydroxide ion. And so you might say, oh, then maybe I'm done. But remember, this question's asking me about, oh my goodness, how many moles of this thing were added to the water. So I need to fill out this ice chart. So this is working kind of backwards because I have this number. Right? And so let's think about what else we can fill in. We know initially that this was 0, this was 0. And actually, we don't know what this is. That's what we're trying to find. So let's call it something. Let's call it X. Normally, we reserve the X for the change line, but that's not the case this time because I actually know that, right? Look, I know that this is increasing by this amount. And it's a 1-to-1 ratio, so is this. Which means that this has to be decreasing by that same amount. So my equilibrium concentration of the ion is going to be X minus that. Okay, so now we know that that number is going to be small in comparison to what X was to begin with, but I have to leave that number in there as I now attempt to solve this equation for X, okay? So let's think about this. I can write a Kb. So now, I know Kb, 3.3 times 10 to the negative 7. I now know that both HClO and OH minus are represented by this number and this number, so multiplied together, that's that number squared. And then my my equilibrium concentration of my base is X minus that. This is a little more involved to solve than perhaps what we've done before. Multiply both sides by the denominator, and we end up with this. Oh, we have to distribute. So 3.3 times 10 to the negative 7x minus 1.04 times 10 to the negative 10th. And then, of course, this is just a number that now I have evaluated. And we're looking for x. So I would take this number to the other side. And we end up with 3.3 times 10 to the negative 7x equal to 9.996 times 10 to the negative 8. And then divide by x. Oh my gosh, divide by 3.3 times 10 to the negative 7. And x comes out to be a pretty nice number here, 0.3. Okay, which is a molarity. And go back to your ice chart, that is the initial molarity of the ion that we're looking for. So, but that's not what, I don't want the molarity, they wanted me to find moles. So if I know molarity and I know the liters, I can find moles. The molarity is now 0.3, that was x, equals moles over, and my initial volume was 2 liters. Take the 2 to the other side, and we should say that I had 0.6 moles of the ClO minus, which means I had 0.6 moles of the NaClO because it was an ionic substance that ionized 100%. Okay, so that was a slightly more difficult question than just a pure straight calculation of like a hydroxide ion concentration from Kb. But still doable with our knowledge of ice charts and